This is the second video for section 20.3, and in this video we're going to be looking at finding equations for the ellipse and as well as some applications. So if we want to find the equation of ellipse, we've got 2 points here. We've got 16, 0 and 0, 6. So this should give us some indication, since we're on the axes here, that these are our vertices, since that's all the information that we have. So if that's the case, we know that our x-axis is actually our major axis because the x-coordinate here is bigger. And our y-axis is our minor axis. And so this tells us that our a value was 16, so then a squared would be 16 squared, which is 256, and that b is 6, so b squared is 36. So if we wanted to go backwards and find the equation for our line, again remember we've got the major axis is x, so we're going to have x squared over a squared plus y squared over b squared equals 1. And in this case, we'll just plug in x squared over 256 plus y squared over 36 equals 1. And that's all we need to do. So let's take a look at an application. The arch of a tunnel through a mountain is semi-elliptical, meaning it's half an ellipse, with a major axis along the ground, so the horizontal axis. The base of the arch covers the entire 50-foot span of the 2-lane road. The highest part of the arch is 15 feet vertically normal, so perpendicular, above the center line of the road. So normal and perpendicular are synonymous in this case. Can a 10-foot wide and 14-foot tall semi-truck pass through the tunnel while staying in this lane? And we're assuming to the right of the center line. So I just want you to pause here for a second, see if you can kind of figure this one out, see if you can at least draw the picture for it, and then resume the video and we'll kind of work through it. So if you thought about this one, you drew the picture. You know the span of the road is 50, the height is 15, they tell us that. So that means if you cut that 50 in half, you get the x, you get the a value there, 25, x is the major axis. Square that, you get 625, so you get x squared over 625. Your minor axis is that 15, that y-axis, so b squared is 225, so you put y squared over 225. And you set that equal to 1. So this is the equation for the tunnel. Now to check to see if that semi will fit through, you can plug in the x is 10 and y is 14. And if you do that, you end up with 232 over 225, which is about 1.03, which is greater than 1. So no, the truck will not fit. So other than going left of center, and you can check to see if that would work, the only other option really is to deflate the tires a bit, because we're really close. Or find an alternative route that doesn't go through the tunnel. So some of the things to kind of keep in mind when design is involved. The next thing we're going to look at as far as applications go is how to figure out how flat the ellipse really is. And we have some formulas for flattening. And really what flattening is telling us how far away we are from the center and how flat the ellipse is. So the flattening formula is f is equal to 1 minus b over a. So you're comparing that minor axis to the major axis. Now keep in mind, b is always smaller than a when we're dealing with an ellipse. But you can see as they get closer and closer together, as those numbers get closer and closer together, b and a, you get more and more circular, so you end up with essentially 1 here, and 1 minus 1 would be 0. So f equals 0 would be a circle, and the highest you can get really is 1 here, so f equals 1 would actually end up being a line. It would be so flat. So again, that B would be getting very small compared to A, and you can see how that would be getting flatter and flatter. Another way we talk about flattening with regards to an ellipse is what's known as an eccentricity. And there are two eccentricities. There's one with regards to the major axis. We call this eccentricity 1. And this is really just comparing C to the major axis, or if you want to plug in the formula for C, it would be the square root of A squared minus B squared over A. And the eccentricity for the minor axis is just C with compared to B. Most people only refer to the first eccentricity when they're talking about it, but it is possible to also compare to your minor axis. And again, if you wanted to plug in the formula for C, it would be A squared minus B squared over B. So let's take a look at an actual real world example, because we're actually looking at the Earth in this case. This is taken from another textbook on surveying, and it gives some of the dimensions that have been approximated for the major and minor axes of the Earth over the years. Keep in mind that the Earth is slightly squished. It's not perfectly spherical. It is an ellipsoid. And so what happens here is that based on approximations, again, you can see in 1866 what the approximation was for the major axes, and the major axis is the equatorial axes, and the minor axes would be the polar axes between the north and south poles. And you can see they're very close. They're only off by about 20,000. And you can see how they haven't really improved greatly. You can even see how these in 1980 and 1984, the changes were so minuscule that they were out to the hundredths of a meter here. But the most recent ones that most commonly used are these ITRS. So we're going to go back. We're going to actually look at the WGS 84. And we want to find the flattening and the first and second eccentricities for these. In this case, again, we're going to be using these numbers here. And we'll start with the flattening. So F is equal to 1 minus B over A. Again, our minor axis B is here. That's our polar axis. So we have 1 minus 6,356,752.3 over 6,378,137.0. So if you go through and calculate all of that out, you should get your flattening coefficient to be 0.00335. And you can see how this is very close to 0. So in this case, it's pretty circular. And that makes sense. Again, the Earth isn't a super squished ellipse. It's just slightly squished because of gravity pulling the equatorial axis out a little bit. If we would talk about the eccentricities, the eccentricity 1, it might be first helpful to find C. C in this case is going to be the square root of A squared, so 6,378,137 squared minus 6,356,752.3 squared. And again, when you put that all in your calculator, you should end up with your foci being about 521,854.2. Again, pause the video at any point if you want to work through these on your own. So now that we have that number, we can find eccentricity 1 is going to be that 521,854.2 over our major axis, 6,378,137, and that comes out to be approximately 0.0818. Again, not very squished, somewhat circular. So this is telling us our focus point is actually pretty close to the axis in comparison to the actual vertex here. So this is our vertex, this is our focus, and we can see how compared to 6 million, this is significantly smaller. So E2, if we go through and calculate, again, we take that same numerator, only this time we divide by the minor axis, so 6,378,137 356,752.3, and we come out with approximately 0.0821. Again, relatively small. We're just comparing it there so that we can talk about how close to being circular we are in this case. So we're going to look at one more example here. Kepler found that the Earth traces an elliptical path around the Sun. So before that, it was assumed that we had a circular orbit around the Sun. And based on the data, he noticed that didn't quite work out. There were all sorts of fixes that were implemented to try to make it circular, but it just didn't work. Anyway, so he found that we had an elliptical path around the Sun, with the Sun actually is one of the foci. It's not actually the center. And the length of the major axis of this ellipse is about 186 million miles. And the first eccentricity of this ellipse is 0.017. So again, it's pretty close to being circular, just not quite. So we want to estimate the closest the Earth comes to the Sun. So again, we're going to draw a picture here. So we'll draw in some axes here. And we'll put the Earth out here. We'll just make this our major axis, the x-axis for right now. And we know that the Earth makes this elliptical orbit. It's close to being circular, but not quite. And so the Earth would be over here at another point, and the distance from here to here is 186 million miles. So that means that our A, in this case, would be half of that. It would be 93 million miles. So we know A in this case is 93. Again, the Sun is our foci, so it's pretty close to being at the center, but not completely there. And so we want to find the distance here that's the closest between those two. So what we're going to do is we're going to use that eccentricity that we had. Remember that the eccentricity is equal to c over a. So we can find that focal distance because we have a and we have e. So we have 0.017 is equal to c over 93. Now if we multiply both sides by 93, and again, I'm just keeping it in terms of million miles because we don't have to write all those zeros out. So this tells us that c is approximately 1.581. Again, million miles. So if we know that c is that distance from the center, again, in comparison to 93, that's pretty close to being at the center. Then we can say that the closest, because that was what it was asking for, the closest the Earth comes to the Sun would be 93 million miles minus our 1.581. So it would end up being about 91.419, again, million miles. If you wanted to figure out the farthest away, you just do the opposite. You'd say 93 plus 1.581, and in that case you end up with about 94.581, again, million miles. So that's pretty far, and again, it's pretty close to being circular. And this is going to conclude the second video for section 20.3.